Hi, pre-Q honors. Okay, so these are your homework problems. Okay, and let's see, what page are these on? These are on pages in your packet, pages 17, 17 through 20. Okay, so on pages 17 through 20, our homework is 2, 3, 4, 9, 10, and 12 through 14. Okay, so we're not going to do all of them together on this video, but again, all the answers are posted in the key, and you could actually do more problems if you need extra practice. We're just going to do some of these together. Let's start with number 3. Okay, so number 3, it says, suppose you are rolling 2 dice, and what is the probability you roll a pair or a 10? Well, there are 6 ways to roll a pair, because you could have 1s, 2s, 3s, 4s, or 6s. And a 10. Well, you could have a 5 and a 5. You could have a 6 and a 4. You could have a 4 and a 6. You could have, let's see, what else? Did I miss anything? Nope, that's it. So you could have a pair or a 10. Now here's the problem. Do you see how you counted something twice? You counted this event twice. Okay, so if you want to count it once, you just don't want to count it twice. So if you count something twice, subtract it once. What about number 4? It says you're drawing one card from a deck of 52. What's the probability of drawing a face card or a black card? Well, again, queens, jacks, and kings all have faces, and there's 3 of those and 4 suits. So there are 12 face cards. And black cards, there are 26 black cards. But notice you counted black face cards twice. And there would be 6 of those because you have jacks, queens, kings, and spades. And jacks, queens, kings, and clubs. So if you count them twice, subtract them once. That was not a mutually exclusive event. Those were not mutually exclusive events. They had an intersection. So there you go. Okay, why don't we do number 9? Let's do that one next. Okay, so number 9, it says, let's see. Okay, there's backup components for vital systems such as electric power distribution systems in case something fails. So suppose that 2 generators each have a probability of 98% of working, and the system will work as long as at least one of the generators works. What is the probability it will operate? So again, what is the probability at least one works? Well, it might be easiest to say the complement, which is none of them work. So wouldn't that be 100% of everything that could happen minus the probability that none work? Or another method that you could have done is the first one works and the second one does not. Or the first one does not work and the second one does. Or they both work. But again, I think that would take a little bit longer. You could do it that way. But why don't we try it this way? 1 minus the probability that none works. So none working, well, if 0.98 is works, what's the probability it works? The probability that it does not work must be 0.02. So the first one doesn't work and the second one doesn't work. So you would end up with 0.9996. That's the probability that at least one works. Okay, why don't we try number 12 next? Go ahead and read number 12. Okay, so it says the probability of passing humanities is 0.90 or is 90%. So the probability of no passing humanities must be 10%. The probability of passing speech is 80%, so the probability of not passing speech must be 20%. And the probability of passing Latin is 95%, so probability of not passing Latin must be 5%. So here goes. What is the probability of pass, pass, and pass? So that would be pass the first one, and pass the second one, and pass the third one. Again, you can leave it just like that if you want, or you can multiply it out. There we go. What about failing all three? Well, that would be failing humanities, and so you multiply, and failing speech, and failing Latin. Make sure you use 0.05 for 5%. Multiply that out. What about the last one? Or the next one, passing at least one. Well, how about that's 1 minus the probability of, what would that be? Wouldn't that be 1 minus the probability of failing all of them? So 1 minus the probability of no pass, or all fail, right? Okay. So that would be passing at least one, because the complement of passing at least one would be failing them all. And lastly, passing exactly one. Well, that one's a little trickier, because passing exactly one is passing humanities and fail speech and fail Latin, or passing speech and fail humanities and fail Latin, or passing Latin and fail speech and fail humanities. So here goes. Passing humanities, multiply because it says and fail speech and fail Latin. Or means add, pass speech and fail humanities and fail Latin, or pass Latin and pass Latin and fail speech and fail humanities. All right, let's just double check that that's correct. Pass, fail, fail, pass, fail, fail, and pass, fail, fail. Yep, that works out. Okay, so you can multiply that all together and you should get 0.032. Okay, that was number 12. Let's try number 13. This one's actually different than the others. So for number 13, they said that you have 1,000 vital parts on a rocket. And if any one part fails, the booster will crash. The rocket crashes, okay? Luckily, each part has a reliability of 99.9%. So the probability that it works is 0.999. So that's pretty high, okay? So let's think about it then. What is the probability that 1,000 parts all work? Well, wouldn't you have to have work and work and work 1,000 times? So 0.999 to the 1,000 power. That is the probability that the rocket does not crash. That's 36.8%. Isn't that surprising that it has such a high reliability for each individual part, but to work, but there are 1,000 vital parts. I don't think I'd want to get on that rocket ship, that's for sure. Only a 36.8% that every single part works. Okay, so for the next question, this is where it gets a little different. It says, what is the minimum reliability needed for each part to ensure that there's a 90% probability of all parts working and not crashing? So again, we don't like 36.8. So let's think about it. Let's say X is the probability each individual part works. Okay, so we're guessing it's got to be higher than 99.9%. So X to the 1,000 equals a 90% chance of every individual part working. So we want work for all 1,000 parts. So if you multiply this out, or I should say if you take each side to solve this, we'd have to take each side of the equation to the 1 over 1,000th power. And you end up with 0.99989, okay? That's what you'd have to have. Okay, good job, everybody.